In this tutorial, we will learn how to do a path analysis model in R. And so to give you an idea what a path analysis model is, here's a path diagram here you can see. And so what we're going to be focusing on in this tutorial is the theory of planned behavior, which is depicted above in this first figure here. So a theory of planned behavior essentially says that behavior is influenced by a person's intention to perform that behavior, and their intention is informed by their attitudes regarding that behavior, the norms surrounding performing that behavior, and a person's sense of control or their self-efficacy regarding being able to perform that behavior. And so we can bring this conceptual or theoretical model of the theory of planned behavior to life by creating a path analysis model. And here is the conventional way in which we can draw out what's called a path diagram, which is where we show using boxes for manifest or observed variables, so things that we've actually measured that are directly in our data set. We can show how we presume or specify that they're related to one another. And we can also show covariances between them, variance components, and residual errors. And this is what we're going to specify and then estimate statistically using a structural equation modeling approach to path analysis in this tutorial. And so just very quickly in terms of common notation for a path diagram, note that the unidirectional arrows here represent direct relations or paths in the path diagram. So this is sometimes why path analysis is called causal modeling. Even though we're not demonstrating or proving causality here, we are saying that we presume that this is the causal direction, at least theoretically or conceptually speaking here. And so we're saying here, for instance, that a person's sense of control, we're presuming is going to predict their level of intention to perform a particular behavior. And then when you see the residual error terms here, this refers to any variable that is an outcome, meaning that there's arrows drawn to it or it's being predicted by other variables in the model. We see residual error, sometimes called a disturbance term here, often represented with the circle with the E in it or for error or a D in it for disturbance. And then you'll also note that we have the little half circle or the double-sided arrows here that point to the same variable. This is an example of how we specify a variance component, so estimating the variance or the variability in attitude. And we see a double-sided arrow here, a bidirectional arrow that's pointing between two variables. This represents a covariance here, and it need not be curved like this, an arc. It could also be straight and depicted in that way as well. Another thing to note in terms of vocabulary is that any set of variables for which there are no modeled causes or specified causes in the model, those are considered exogenous variables. And any variable that has an arrow going to it, meaning that there is a modeled or specified cause to it in the path diagram or the path analysis model, that is called an endogenous variable. So endogenous variables will have residual error. Exogenous variables will not. And it's common practice that with exogenous variables, we allow them to covary. And you can see that here as depicted with the covariance terms. And when we allow something to covary, that'll automatically estimate in most statistical software programs, and specifically in the package we're going to be using called Lavon today, it'll estimate the variance components as well. Now, what's also important with path analysis is that when we don't draw arrows or we don't specify a relationship, what we're implying is that we're saying there is zero association between these two variables. So notice there is not an arrow from control to behavior in this path diagram. And so what we're saying here is that essentially there's the directional relation path here is set to zero. Okay, so there is an implication in terms of what we do not draw in terms of possible associations in the model. Okay, so now that we have this common vocabulary out of the way and we understand what a path diagram is, now it's time to jump into actually doing this in R and using a package that is called Lavon. So the first thing that we're going to do is I'm going to note that we're doing path analysis in R here, and I'll note that we're going to be using primarily a structural equation modeling approach for path analysis, but I will show you some equivalents early on in terms of how we can run a multiple linear regression model as we traditionally would using, for instance, the regression function from the less-r package or the LM function from base R. We can do the same thing and get the same results in a path analysis framework using a structural equation modeling framework. Okay, so the first thing we're going to do is we're going to set our working directory. And so I'm going to set the working directory to my H drive, and this is my R workshop folder. I'm going to run that. And this is where I've saved a data file for this tutorial that's called plan behavior with a capital P and a capital B. It's a .csv file. It's saved in my R workshop file or folder, which I've set as my working directory here, and you can see that verified. If you go to session, set working directory, choose directory, you can do that manually to select the folder that contains your data file that you're going to be reading in. So that brings us to the next step, read in the data. Okay, so we're going to use the reader package for this. And so we're going to use the library function and the reader package in quotation or in the parentheses there as a sole parenthetical argument. If you've never installed this before or you haven't done so recently, use the install.packages function from Basar, and then you would type in quotation marks, the name of the reader package, so READR, in the quotation marks there as a sole parenthetical argument, and this will install the package, so then you could run this. I had already installed the reader package, so I was ready to go there. Okay, now it's time to read in the data and name it and assign the data to a data frame object, and I'm going to call it DF, just for data frame, very generic there. Use the left-handed arrow here operator in order to assign the values we're going to read in to this object so we can reference it later. And I'm going to use the read_CSV function that comes from this reader package that we just accessed here. And so now here's where I type in the exact name, or copy and paste in the exact name of the data file that is located in my working directory folder here, which this one is called plan behavior.csv with a capital P, capital B, all one word. And make sure you have that .csv extension there. Let's click run. Okay, so we've read in the data. Let's take a look here. I've got some other things visible there in my global environment. Some other data frames I've previously read in. And so let's take a look here, and you'll see that we have the 5 variables which correspond to that to the path diagram we just saw: attitude, norms, control, intention, behavior. Just note that these are all lowercase here. And so we're going to specify that path diagram, ultimately what we're going to do in this tutorial. But first, we'll do a more condensed version of it just to show the equivalence between a standard multiple linear regression model and a path analysis and how we can get the same results using either. Okay, so we'll do that first. So showing equivalence between multiple linear regression and SEM, structural equation modeling approach to path analysis. Okay. All right. So the first thing that we're going to do is we are going to install, using install packages, the Lavaan package. That's all lowercase Lavaan. And I've recently done this, so I'm not going to run this, but you'll likely need to run this line of code here if it's the first time you've ever installed the Lavaan package or you need to update it. But I will use the library function with Lavaan, all lowercase, as the sole parenthetical argument so I can access that package and the functions within it. So I'll click run there. And so in terms of how you specify a model in Lavaan and then ultimately estimate it and summarize the results, I'll show you those steps here. It can be a 2-step process or even a single if you really nested some functions, but I think it's helpful to break it out in this way. So the first thing we're going to do is we're going to specify just a simple model here. And so what I'm going to do first is just create an object that's going to contain the model specifications. I'm just going to call this spec mod for a specified model here, all lowercase. And then I'm going to type the quotation marks. And I could do this on one line, but I'm going to spread this out into multiple lines here. And so within the quotation marks here, I'm going to specify just a simple linear regression, multiple linear regression model here. So it's actually a multiple linear regression model. And I'm just going to do the first part of our path diagram here just to show. It's going to be attitude, norms, and control predicting intention, or in other words, intention regressed on these 3 presumed predictor variables there. And so I'm going to type in intention. We're going to use the tilde symbol. It's that squiggle symbol here That's the regression symbol that we would typically use in our regression functions in R. And then I'm going to type in the names of the three predictor variables or presumed predictor variables as part of that model. So they are attitude, norms, and control here. I'm going to use the plus sign operator to add additional variables here. So this is an additive model. Okay. And so the next thing that we can do is we can run that. And so what this has done is this has just assigned this specified model here to this object called spec_mod. And this will allow us to reference it in the next step. And so the next step, this is where we're going to estimate our model. And here we're going to want to create a name for the model we're going to estimate. And I'm just going to arbitrarily call this fit_mod, all lowercase there, one word, no spaces. And I will use the left-handed arrow operator there so we can assign the estimated model to this object here. And this is where we're going to introduce a new function. This function comes from the Lavon package. It's called SEM for structural equation modeling. It's all lowercase. And as the first argument, we're going to enter the exact name of our specified model here, which is spec_mod. So that's our first argument. And then our second argument is just data equals and the name of our data frame to which the variables in our specified model belong. And so this will look somewhat familiar to what you've done before using regression-based functions as part of various packages in R. Okay, so now we're ready to run this line here and assign this, what is a specific type of structural equation model, which is a path analysis model. We're going to assign it to this object called fit_mod. So let's run that line of script there. And now we're ready for the third step, and this is when we're going to summarize the results. Okay, and so in terms of summarizing the results, we're going to use the summary function from base R, which may look familiar to you because it's the same one you would use if you're using the LM or the linear modeling function, which we'll use in a second, from base R. And so what we're going to enter as our first argument is the name of the estimated model object. So we'll paste that in, comma, and the second argument is going to be, we're going to request some additional information we'll get. So let's do fit.measures equals true. And then as our third argument, r² equals true. And so what this is good, the first one, fit.measures equals true, this is going to request model fit indices. What we're specifying here is going to be a just identified model, meaning that it has degrees of freedom equal to 0. So the fit measures, these aren't going to be of interest for us here, because this will be what we call a saturated model, meaning that there's no degrees of freedom with which to assess fit in terms of goodness of fit of the model to the data using some absolute and some comparative or incremental fit indices. If you're wondering what those are and you want some more details on that, check out the corresponding conceptual lecture video for path analysis. Now the r² equals true. This is where we're just going to request the r² value, which you would is going to request the unadjusted r² value that we're accustomed to in typical regression-based functions from R. All right, so if we run this line here, we will get the summary of our model here. Okay, so here you see it notes that the version of Lavon, it tells us that it ended normally, so everything worked fine here. It tells us the number of free parameters in our model, so 4. And then it tells us here that we have 0 degrees of freedom, which indicates, you can see that here, 0 degrees of freedom, that this is a just identified model, meaning that we've basically specified every relation that you could have here, and that the number of unique or non-redundant sources of information in the covariance matrix that goes into this model is equal to the number of free parameters that we've specified here, okay? And I'll show you what the free parameters are here down below. Notice here too, it indicates the number of observations, which in this case is the number of employees. So we have 199 employees that were retained for this analysis. We're going to skip through the other model fit indices here because this is a just identified model, meaning that it doesn't have degrees of freedom greater than 0, which means that we won't be able to interpret these fit indices. And we can just go straight to the regression section here, which you can interpret like a normal regression model output. And so here you can see the associations between each of these predictor variables and the presumed outcome variable here. So you can see attitudes is positively and significantly associated with intention to perform the behavior. Norms regarding the behavior is also, as indicated by the estimate here, the path coefficient estimate or the regression coefficient estimate is positive, and the associated p-value is less than 0.05. So this is also statistically significant and positive. And the same goes for the control predictor variable. It also significantly predicts and positively predicts the intention variable here. And so here are the first three free parameters or parameters we've estimated in our model. And this right here in the variance section, because that has a little dot in front of it, this represents the residual error or the disturbance term that I mentioned previously. And so this is the residual error here, and you also get its significance value, which is usually not of substantive interest in this case. Now, this is something that we don't specifically get or explicitly get when we run our typical regression-based functions in R, but we do get it here. And so we do see also that we have our R squared value for the intention variable, which is our outcome variable, and it is 0.369. This is unadjusted R squared. And so this would indicate that collectively attitude, norms, control explain about 36.9% of the variability in intention for this sample. Okay, so that's how we can specify this using a path analysis model framework within structural equation modeling. And we could also specify this in a slightly different way too. So what I'm going to do now is just copy the script we just made there. I'm going to paste it below, and I'm going to do a little tweak here. And so note here that I haven't specified the covariance terms. So if we looked at this here, notice that here we could specify the covariance terms as well between these exogenous variables, meaning that they don't have a depicted or specified cause in our model here. And so we can do that. And if we actually specify these covariances, the function will automatically estimate the variances for us as well, because in order for something to covary, it needs to have variability. Okay, and so how do we specify a covariance if we want to explicitly specify this in our model? Well, we'll use the double tilde symbol. And we just do this for the exogenous variables, which are these three, which are not predicted by anything else in the model. So what I'll do here is just copy these three predictors, paste it below here, and I'll replace this first plus sign with the double tilde. And so what this is saying is allow attitude to covary with norms and control. And then I'll create another line by copying and pasting these and replace this plus sign with two tildes to represent variances. And I forgot the in and norms there when I copied and pasted. So these are the three possible covariances. So we have the covariance between attitude and norms represented here. So attitude and norms, attitude and control. We have that represented here. And then norms and control. So there's three possible covariances that we can estimate between these three exogenous variables there. Okay, so let's rerun the script. We don't need to change anything else there, and let's see what happens. So let's run that. Okay, let's take a look and see how our script is different. Okay, so now notice, whereas before we saw 4 free parameters here, now we have 10. Okay, but notice our degrees of freedom are still equal to 0, meaning that this is still a just identified model. So we're not going to interpret this model fit index information here. Instead, we'll just come straight on down to the regression section, and all of these regression coefficients or path coefficients should look familiar because the p-values, their estimates, and their standard errors are exactly the same as the previous model in which we did not explicitly specify those covariances. And also show you below, we also get the variances here. But now you'll see we have this section called covariances, where we get the estimated covariances between our predictor variables here, and you get their p-value, their level of significance. And you would interpret that just as you would a normal p-value for a hypothesis test. And then here, note that we don't just have the residual error, the disturbance for the intention outcome. We now have the variances for these exogenous variables as well, which are attitude, norms, and control. And so you get their variance components there and the associated p-values. Now, often these are not going to be of substantive interest here unless we explicitly had hypotheses regarding some of these exogenous variables, these predictor variables correlating with one another, or perhaps we were concerned about the amount of variability in some of our predictor variables. And note that the R squared value remains the same even when we specify those covariances between the exogenous variables. Okay, so that's just to show that you can specify these models in different ways. Now, let's see how we can specify this same model using just a standard linear modeling, standard regression, multiple linear regression framework. And so we'll do the same thing we've done before. We're going to specify and estimate our model. Okay, and so let's just call this fit mod. It'll override the existing object. We're going to use the LM function. The LM function, the linear modeling function, which is one way in which it's from base R, it's one way in which we can estimate a simple linear or multiple linear regression model. And we're just going to type in the exact same regression formula we've been using before. So intention regressed on attitude plus norms plus control, comma. So our first argument is our regression model here. Our second argument is data equals df. That's the name of df is the name of the data frame to which these variables that we've specified here belong. And then I'm going to add a line here, so summarize the results. And we will do summary, same summary function we use from above, and just type in fit mod here. Okay, so the name of the object we're specifying here. Again, it'll override the previous attempts that we've done there with the SEM function. So let's just go ahead and run all this together and take a look at the output. Okay, so we get much less output here. Again, this is just a standard multiple linear regression model here run in a linear modeling framework, a linear regression framework. And notice that while the decimal places are reported further places out past, or the number of digits past the decimal is more than what we saw by default in the SEM function from above. Here we do see the exact same regression coefficients here. So we see those and we get the exact same p-values. Again, there's some rounding differences here. And then you'll notice too, the R squared, this is the unadjusted R squared value, is 0.369, which we saw above. Okay, and then that intercept value, which we saw in the previous model, is here you can see it's the intercept value is not going to be explicitly modeled here in the linear regression model. In the linear regression model function, it is explicitly modeled, but it's not explicitly modeled here in our standard path analysis. Now, there is a way in which you can request that, and there's a different notation you could use if you really did want to get the intercept estimate for our path analysis model, which is in that structural equation modeling framework there. But as you can see, everything's equivalent here. You can do a path analysis, a simple path analysis like this with a single outcome variable and multiple predictor variables. You could run it in a structural equation modeling framework, or you could run it in a standard multiple linear regression framework as we did here, and the results are going to be statistically equivalent. And it's really up to you how you want to do it. But where the path analysis does depart from multiple linear regression is when we want to estimate a model with multiple outcome variables, and as well as a model that might have a variable that serves as both a predictor and an outcome variable. If we want to model those simultaneously in the same model and assess the model fit, that's when we have a major advantage when we go with the structural equation modeling framework approach to path analysis models. Okay, so now I'm going to make a note that we're going to test our focal theory of planned behavior, TBP, or TPB rather, model here. And so I'm just going to go up to above here. I'm going to grab what we did, the last thing we did with that SEM function there. Okay, so I'm just going to copy that. So what I've grabbed here is this. So right before we came to the LM function, we specified this model, and I'm just grabbing the one in which the covariances are explicitly modeled here. So I'm copying this chunk where it's both the model specification, the model estimation, and the summary of the results. And we're just going to tweak this a bit. So I'm going to paste this below. Okay, so what we have here is we've specified the first part of this model, But now we also need to note that there is this link, this proposed directional relationship between intentions and behaviors as part of the theory of planned behavior. So we need to specify that equation as well. And so what we can do is you could do this anywhere. This isn't in particular order. In fact, you can even make notations within this. I'm going to say directional relations here, okay, that are going to come below this. Okay, and so the directional relations are the ones we already specified here, where we had attitude, norms, and control predicting intention. And now we're going to have behavior being predicted by intention. Okay, that's behavior is the name of our fifth variable there. Okay, so these are the directional paths here. So we can estimate these equations simultaneously, these structural components of the model simultaneously, when we have a structural equation modeling based framework for our path analysis. And then I'm going to make another note here and say these are the covariances. And we're just going to keep these as is because these are the only exogenous variables here, attitudes, norms, and control. So we're going to allow them to covary. And again, by default, this will estimate our variance components as well when we add in the covariances here. The variance components, I should say, for the exogenous variables, which again are those variables that have no specified cause in our model. It's like a true predictor variable, okay? All right, so let's go ahead and run that. We can come down here to our estimate model, and we don't need to change anything. We're still using the same object name, spec mod here. If you changed it, you need to change it here. We're just referencing that in our SEM function, saying, okay, now let's estimate this model we've specified here, and the data equals name of the data frame to which all these variables belong is df. And we're using the left-handed arrow to say we're going to assign this estimated model to this object that we're going to call arbitrarily fit mod. So let's run that. And then finally, we're going to summarize the results using that summary function again. And so here we're going to put this object fit mod, which is our estimated model here, copy that in and paste it as our first argument. And then as I mentioned before, I recommend including this fit.measures equals true to get the global model fit indices, because this time it'll become relevant because we're going to have what's called an over-identified model, which means we can assess the model's fit to the data using some of these absolute and comparative or incremental fit indices. And then also request the R-squared value too, because that's nice to have. So let's go ahead and run the summary and take a look and see what we've got here and interpret the output. Okay, so we've got a lot of output here. So here's the number of free parameters. Okay, it's equal to 12. And how do we come up with that? Well, if you really want to know, the way that that's calculated is simply using this formula here. So we have 5 variables, right? So we have intention, behavior, attitude, norms, and control. So 5 unique variables. And if we want to know essentially how many unique covariance and variance components are in the covariance or correlation matrix between those 5 variables, so if you imagine the lower diagonal of a correlation or covariance matrix between them, there's actually a simple formula we can use to estimate that. And that is that we take 5, the number of variables, times the number of variables, so 5 plus 1, okay? So all you have to remember is the number of variables, 5, times the number of variables plus 1, and then divide that by 2. And if we run that, or rather here, oops, forgot to put the times symbol there. So 5 times 5 plus 1 divided by 2, and we run that, we get 15, okay? So that's the number of unique, I'll make a note here, unique, non-redundant sources of information for our model, okay? And then if we want to know the number of parameters in the model, that's just where if we come back to this image here, the number of parameters for the model is going to be, I'll make a note here that this was 15. So now let's go to the number of parameters in the model. This is all done automatically for us in the model estimation, but this is just to give you an idea what's happening behind the scenes. We would just count up all the unique parameter estimates, where parameter estimates include the residual error terms, the directional relations we've specified in the model, and the variance and covariance terms. So if we count this up, so we have 1, 2, 3 variances, 4, 5, 6. So when we add in the covariances, Let's move on to the directional paths here. 7, 8, 9, 10 directional relations here, or path coefficients. So we're at 10. And then 1, 2 residual errors, so which would be 11, 12. So we have 12 parameter estimates. Okay. And so if we take the first, so the number of non-redundant or unique sources of information in the model minus the number of free parameters, or parameter estimates for short, we get 3. Okay. And so this means that our degrees of freedom, which is often abbreviated as DF, is equal to 3. So this value is greater than 0, which means that this model is over-identified. And when you have an over-identified model, that means that you can actually interpret the model fit indices that we're about to talk about. Okay? All right, so let's take a look at the output that we saw earlier here. So here's the number of free parameters, or parameters is 12. We calculated that by counting it up. And then remember, 15 minus 12 gives us 3 for the degrees of freedom. So we see that verified. The model does it for us automatically. Okay, so what we're going to do is we're going to work through 5 common model fit indices that help us assess the extent to which the model we've specified fits the data. Okay, and so we'll start with the chi-squared, or chi-square test. And it's not super nicely labeled here, but if you look at the model fit statistic, this is the chi-square statistic here, the chi-square value. It's 2.023. It's not very informative here to see that by itself. What we're really interested in is that chi-square in relation to the degrees of freedom, which gives us a p-value of 0.568. So the chi-square test here is, it's actually the null hypothesis is a model in which is that the model fits the data perfectly. So it's a model that fits the data perfectly. And so what we're saying is that if it is non-significant, meaning the p-value is equal to or greater than 0.05, we are failing to reject the null hypothesis that the model fits the data perfectly. So in other words, we have reason to believe that the model does not fit significantly worse than a perfect model, which makes us feel reasonably confident that this model has probably pretty good fit to the data. Now, if we did find a p-value that was less than 0.05, that would have us reject that null hypothesis that the model fits the data perfectly and lead us maybe to start concluding that, in fact, this model is perhaps not a great fitting model. Now, the chi-square test is notoriously is very sensitive to sample size. And so that's something to consider as well. The bigger the sample you have, the more likely you're going to find that your model doesn't fit well. Okay, so, but at least in this case, we have support here. So support that model fits data. Okay, so the next thing that we're going to do is we're going to come down here and look at the comparative fit index here. I'm just going to copy this exact text there, paste. And the comparative fit index, what we're looking for here is for this to be 0.90 or higher. That's the conventional cutoff. And you see it is above that. It's 1.00, which is greater than 0.90. So we would say this also supports that the model fits the data. And I'll add to the chi-square here that the p-value was greater than 0.05, and that's how we knew. And here, the CFI value is greater than 0.90, which is the conventional cutoff. And now we're going to come down to the Tucker-Lewis index, or the TLI. I'm going to copy that and paste this here just to make this clear for us. And the conventional cutoff for this is if the model, or if this index TLI is 0.95 or greater, the model fits the data well. And so here we see we get support for that because it is greater than 0.95. So let's paste that there. And so with the TLI, the conventional cutoff is 0.95, although sometimes people might relax that to 0.90 like the CFI. And then we're going to scroll down. And so these two, the comparative fit index, Tucker-Lewis index, these are measures of incremental or comparative fit. So we're comparing the model to a null or independence model here. And then we can move down here to our model fit indices that are absolute in nature. And the first one we're going to look at is the root mean square of approximation. Paste that there. And often this is abbreviated as just RMSEA. And so we're going to find here that model fits the data. Okay, and the reason we're just going to say that is that the RMSEA is less than the conventional cutoff of 0.08. Sometimes people relax that to 0.10, but typically it's going to be RMSEA is less than 0.08. Okay, less than or equal to, I should say. And so in this case, this is actually sometimes called a badness of fit measure. So we're actually looking for values that are below 0.08, which we meet that threshold there. And then finally, the last model fit index that we're going to look at is the standardized root mean square residual here. Copy that, paste it here. And often it's abbreviated as SRMR. And here again, we're looking for the model fit to be less, for the index to be less than 0.08. And we do see that it's 0.019. So this is another instance in which we're looking for it to be less than that value of 0.08. And so this is a rare occasion in which all 5 of these fit indices, the chi-square test, the comparative fit index, the Tucker-Lewis index, the RMSEA, and the SRMR, are all meet the conventional standards for good fit to the data. So this is often you'll run across in a situation where 1 or 2 of these, if not all of them, will not fit the data. If only 1 or 2 don't quite fit the data well, then you probably have an argument for the model still fitting the data reasonably well. But if you run into a situation where almost all of these or most of them do not meet the conventional cutoffs, then you probably have an instance in which the model is not well specified and doesn't well depict what's actually happening in the data. Okay, and so here, once you do find that reasonably you can make the argument that the model fits the data, then you're ready to come down and actually interpret the model parameters or the coefficients. If you don't find that the model fits the data well, you should really stop there and then go back to the drawing board and say, have we specified this model correctly? Is there something that isn't making theoretical sense here? And should we revisit that? Okay, so now we'll come down to, just as we did before, the regressions. And so now you'll see there's 2 regression equations here. The one we saw before, which is attitude, norms, control, predicting intention, first part of our model. And we see that, these path coefficients here, or directional relation coefficients, regression coefficients, are all positive. They're all statistically significant. Their p-values are less than the conventional 0.05. And now we have this new direct relationship here, which is intention predicting behavior. And we see that its estimate is also positive, and we see the p-value is less than conventional cutoff of 0.05, so we'd say it is also statistically significant. Okay, and then we get our covariances here between the exogenous variables that we specified, and we get the dot intention, dot behavior. These are the residual error variances or the disturbance terms here. And then we get the variances for the 3 exogenous predictor variables as well. Note here, now we have 2 r-squared values, one for the intention variable. Okay, that's our first outcome. So if we look here, just to remind ourselves, intention is the first outcome here. So we can look at the variance explained by these 3 predictors in relation to intention. And then the second r-squared is 0.198, and this is for behavior. And so this is the amount of variance explained by intention in behavior. Okay? And so this is how we can estimate a model simultaneously using a structural equation modeling approach to path analysis. You could also do this using a multiple linear regression model, but you need 2 of them. You need to estimate 2 separate models here, and you wouldn't get these overall estimates of fit here, model fit to the data. So what's great about this is we can start testing theoretical propositions and also causal chains of variables as well, or what I should say are presumed causal chains of variables. So just because we find evidence that this predicts this in the model here, it doesn't mean that these are true causal relationships because there could be some third variable that's actually explaining this relationship here, just like we would with any kind of correlational design. But this is a way to test theory and is a way to look at process as well and to test more sophisticated and advanced models. Okay, so the one thing I do want to mention that I haven't touched on yet is what are the statistical assumptions here? So the statistical assumptions for this approach to path analysis we're using are going to be, well, first I should say they're going to be the same as multiple linear regression. So if you wonder what those are in terms of things that are related to normally distributed residuals and so forth, at least how we're estimating this model here, then check out the tutorial called Multiple Linear Regression in R to learn more details about that. But there are some special additional statistical assumptions that need to be met when it comes to path analysis. And rather than you wait for me while I type these out, I've actually already written them out here, and I'll just paste them below. And they are as follows. So the first is that with the exception of the dichotomous predictor variable, the variables in the model need to have an interval or ratio measurement scale. So when we're dealing with path analysis, where we're dealing with these observed variables here, and the observed variables in our case being intention, attitude, norms, control, and behavior, they need to be relatively continuous in nature. And you can get away with having a dichotomous predictor variable, such as if you had gender coded as 0 for man, 1 for woman, you could get away with that. But otherwise, you haven't met that assumption if you have an ordinal or a nominal measurement scale variable in your model. The second assumption is that the variables in the model are free of measurement error, meaning that we're assuming that they are perfectly reliable. Now, there is a whole other world of structural equation modeling where you can start incorporating the measurement structure as well, which can help account for unreliability in some of the constructs or that we're interested in. And that would require using the actual item level data and then creating what we call a latent factor. So it's not observed, it's something that we're inferring from the items. And so that gets into a whole nother world of latent variable modeling in not just R, but in statistics in general. And but if we're using a simple path analysis like we're using here with observed variables, then we assume that these variables are free of measurement error. How tenable is that? Well, we know that nothing is perfectly reliable for the most part, especially when we're measuring humans. And so that's often when we relax there. But it is something to keep in the back of our mind that this could affect the extent that our findings in our model and the degree to which certain variables are related to each other. And in particular, it can attenuate the potential strength of the relationships we see between different variables. The other thing in this case, we are looking specifically at recursive models, meaning that if you look here, we don't have any arrows where there's an arrow pointing from attitude to intention and then a second arrow that's going from intention to attitude here. That would be a bidirectional association here, meaning that there might be some kind of feedback loop or something like that. Our model's recursive, meaning that the flow is in one direction from one variable to the next. Okay, so that's something to consider too. If the model was non-recursive, it'd mean that you have feedback loops and things like that. It would also mean that you might have correlated an exogenous variable with a residual error term of a variable that it's actually predicting. Okay. And so that is not something that we're doing here. So that is not what our assumption is, that the model is recursive and that things are unidirectional in our model. Now, the fourth statistical assumption is that the residual error terms are not correlated with each other. Okay? And so what that means is that you don't see a correlation or a covariance between the residual error for intention and the residual error for behavior. And then finally, the directional relations. So those are the single-headed arrows here. These are both linear and additive, okay? And so that's what we're modeling here, is a linear additive model. And this gets fairly explicit here when you see the plus signs there, okay? But our assumption is that these are linear associations. Okay, now I haven't talked about some other things that you might want to specify as well. And that is, there's different ways we can specify the models that we've had here. And so I'm just gonna focus now. I'm gonna grab this chunk right here. This is just one of the randoms model specification syntax that we made here. So this is for our last model. And I'm just going to paste this below and show you some examples of equivalence here. Okay, so I'm going to save this for later, put this down here. But for now, we'll focus on how we could specify this model here. So this is, let's call this approach 1. So approach 1, so we have our two separate equations here, and we use the plus sign to note that we have more than one predictor variable predicting intention. Well, we could also do this using a second equivalent approach. We'll get to the same solution, and that would be that we are going to do each one of these as seemingly separate equations. It's really gonna, the program's smart. It knows that when we have the same outcome variable here to roll these all up into a single equation. But this is equivalent to what we did above here. So we could have just specified it like this. Intention regressed on attitude, intention regressed on norms, intention regressed on control, as opposed to doing intention regressed on attitudes plus norms plus control. This gets us to the same end here. Okay, another thing I want to show you is that that's focusing on the right-hand side of the equation there. Well, we can also, let's imagine for a second that we really, and I'll delete this second part of the model here, that let's assume we have a model where attitudes, norms, and control are predicting intention, but also behavior directly. So the direct relations are as follows. Well, we could write it out like this. You can actually use the plus sign to the left side. In a path analysis framework, you can use this to the left side of the tilde symbol here. So this would be the outcome variables. And so what this is doing behind the scenes here is it's going to estimate attitude in relation to behaviors, norms in relation to behaviors, control in relation to behavior, and then it'll do the same thing with intention. Now, alternatively, we could write it out like this. I'm just going to copy this here and just replace the behavior down here, or intention with behavior. This second approach here is it gets us to the same solution here. So these are equivalent here. You could write it very efficiently like this, or you could break this out into each separate direct relation there. And so you see that here. So now we have behavior in relation, or attitude predicting behavior, norms predicting behavior, control predicting behavior. It's the same thing. Okay, so we have a lot of flexibility there. Okay, so the next thing that we're going to do is I'm going to just copy that, paste that there, and then add a quotation mark under there. So let's talk about covariances. Okay. So we in our model specified the covariances using an efficient format like this. There's three possible covariances between these three variables that we could model, and which we did model here. So attitude covaried with norms and control, norms covarying with control, and we use that double tilde symbol there to note that. And so here we use the plus sign when we want to look at the covariance of this same variable in relation to more than one variables. So that would be approach 1 we could use. The alternative approach we could use, I'll call this approach 2, and I'll copy this, is we could write these all out separately on separate lines here. And so I'm going to take attitude, instead of having attitude covaried with norms plus control in the same line, I'm going to change this into 2 lines here. So now we have attitude covarying with norms, attitude covarying with control, norms covarying with control. And so again, these 2 approaches, 1 and 2, are equivalent. Now finally, let's talk about the variance components. So in our model, we didn't have to explicitly, when you're using a covariance between 2 variables, the program will, or the function will automatically estimate the variance. And so we saw that here. But you can specifically specify the variance if you'd like. And so I'm going to show you how you do that. So I'm just going to copy that, paste this below, get rid of that. And tidy up there. Looks like I had some extra quotation marks there. We're throwing some things off. Okay, so what if we want to just specify, so here it happened automatically in our output, the variances. Well, how do you specify a variance if you just want to make it very explicit in your model process, even though this will be done by default in most cases, if you have a covariance. If you want to estimate a variance when it's an exogenous variable, and there's only one exogenous variable, you would actually need, in that case, at least within the Lavon software, to explicitly specify that variance component. So to specify the variance component of attitude, we would just do attitude, double tilde, and then attitude, okay? So you're just essentially covariating the same variable with itself. So this is just another way of saying the variance here. Okay, so we've got the variance of attitude. And we'll do the same thing with norm or control here. So if we do control double tilde control, this is the variance component for control that we're directly specifying there. And the same thing for norms. So norms double tilde norms. Now we specified the variance component there. Okay, so that's how you do it if you want to specify the variance. Now, I'm not going to get into how you specify a latent variable because that's beyond the scope of this initial entryway into path analysis in R using the Lavon package. And that is a whole nother world that you can use, a whole other world you can enter in terms of confirmatory factor analysis using structural equation modeling, latent growth modeling, latent change score modeling, growth mixture modeling, latent profile analysis. The list goes on and on and on. And these are some more advanced forms of modeling that can be offer some great ways to model data, especially when we are interested in modeling latent variables or latent constructs and accounting for measurement error and unreliability of the different measures we might be using. All right, so this wraps up the tutorial on path analysis in R using a structural equation modeling framework. Thank you.